Hello, good evening all. So we'll go to that interactive live session on week 5 videos. So first of all I'll explain, I'll just give the recap of week 5. Okay, so in week 5 videos there are shape from focus topic, then depth from defocus topic, then about motion blur. So shape from focus topic is a wide area, like it has so many derivations and all. So you have to thoroughly go through that shape from focus to get an idea. So we'll first go to shape from focus topic. So the meaning is shape from focus. Meaning is that we'll find the shape or depth from the focus measure. Depth from focus measure. So we'll have a stack of images. Say we have 100 images, 1, 2, etc. 100. That is taken using a telecentric setup, like a microscope. So an object will be placed, that is to be imaged, and the microcentric setup. In the microcentric setup, we will change the position of the lens to get different images. So first of all, the lens will be here itself, and will take an image. And after that, either the object is being moved or the lens will be moved to get other images. So we can say that in each of the case, the object is at different distances, is it? So there will be a plane of focus for the setup, and at a particular time, a particular region of the object. So say this is the object, this one is the object. So at a particular time, a particular region of that object will fall on the plane of focus. So at this condition, these 2 points, this area will be focused. Okay, then if the object is here, then this portion of the object will be focused. When this object is here, nothing will be focused, no. So we'll get a number of images like this, 1, 2, 3, etc. 100. In each of the case, some say in image 1, some portion will be focused and some portion will be blurred. So in image 2, some other portion will be focused and some other portions will be blurred. So we can say that the overall object points will be focused in some or other image. Okay, so from this stack of images, we have to find the depth of the object. So how can we find? So we can take an image 1 first. Okay, take image 1 first. Then at every pixel location, we can find the focus measure. Then in some pixel location, its focus measure will be very high. That means, say this green pixel is what we are looking for. So this pixel location is 10, say. So and the name we can give it as A. So the pixel A has highest focus measure, or the focus measure of pixel A at image 1 is higher. But in the case of image 2, the same A may not have that much focus measure. So we can say that the point A is focused at image 1 than image 2. Like that, we can find the focus measure of every other pixels, like this blue. Okay, so what we are doing, for every pixel we will find the focus measure at every frame. Consider a single pixel here. Okay, then for that we will find the focus measure at different frame. So it is frame number 1, frame number 2, frame number 3, frame number 4, etc. Then this is the focus measure. So in frame number 1, point A has maximum focus, and after that its focus measure decreasing, right? Then in the case of blue, say it has focus measure high at frame number 3. Okay, so like this we'll get different this focus measure graph for every pixel. So for a particular pixel, say we are getting a graph like this. So from this we can say that either we can take the highest focus measure. So if the graph is like this, we can take this highest focus measure and we can say that 0, 1, 2, 3, 4. At 4th frame it is maximum. So we can will know the depth delta d. Delta d is the distance by which we are changing the object distance or the lens distance. Okay, so delta d is what we are changing. So we can say that at the 4th image plane it is focus. So total depth is equal to 4 into delta d. So that pixel is at the depth of 4 into delta d. Okay, then take another pixel, green pixel. For that focus is at say it is at the first image, then we can say that its depth is 1 into delta d. So like that every pixel will get some different depths. Okay, so depending on the distance from the lens we'll get different focus measure for every pixel. So using that data we can get the shape of the object. So that is the aim of this shape from focus. So here focus measure I am explaining. So here we have 1, 2, 3 and 4 images. Okay, and we are plotting focus measure values of point A and B. Okay, A is orange colored and B is green colored. Then at we can measure the focus measure at every pixel at every image at the pixel position orange position. Okay, then we can say that at 33 at delta d at distance 33 orange has lesser focus measure. Okay, but at 34 orange focus measure increased and again it is increased, and at 36th frame or 36th distance its measure is reduced. So either we can take this as depth. Okay, then in the case of green one, so this one was the focus measure. So we can say that this thing has the highest depth. So this 34 can be taken as the highest depth. Okay, so this way we can take the depth. So the original value can be taken as a depth, the maximum value, the distance at which the maximum value of the focus measure occurs can be taken as the depth, or we can use Gaussian interpolation for finding the absolute value of the depth. Okay, so that thing we can explain later. So how can we find the focus measure? That is the next question. So we can directly find using some operators. First one is pointwise operation. Pointwise operation means grayscale value. We are finding the grayscale. So grayscale values are already there. So by using those grayscale values only as the measure of focus, it may not be accurate. No. So it is seldom used. Then the next one is variance. Variance can be found out by subtracting the mean from the original intensity value and square it. So this way we can find the variance, and variance will be a measure of focus. Okay, then comes the third one is energy of gradient. Here we are using first first order derivative, like fx of z means dou f by dou x in discrete form. Okay, fy is dou f by dou y in discrete form. So we'll find the first derivative. So for finding first derivative, we'll use some kernels. So that is already described in the videos. So the first order kernels can be written as sorry. So we'll discuss the second order derivatives. Okay, so and the next thing is Tenegrad, that is based on Sobel mask. So Sobel mask is like this. So by using Sobel mask on the image, we'll find this thing and this thing, then square and sum. Okay, then we'll get the focus measure. So on every image, we'll find this filtering using some specified kernels. And what do you mean by this filtering? So convolution using these specified kernels will do. So say here we'll take f of z, the image itself, then we'll take this kernel, Sobel kernel, and we'll convolve to get the output. So that output will give the focus measure of the center pixel position. So that will mark on the graph, and again we'll take another pixel, find this focus measure, then we'll mark on the other graph. Okay, so for every pixel we'll find the focus measure. Then the next one is Laplacian of Gaussian. So this is given here. Next one is energy of Laplacian. So here fxx of z is and plus fyy of z. So it is dou square by dou x square plus dou square by dou y square. This is Laplacian, no? So and we are finding the square of it. Then the name will be energy of Laplacian. So here LOG is, will first filter using Gaussian filter and then using Laplacian on the filtered image. So these all operators will give the measure of focus on a particular pixel. Okay, then the next one is one important measure, that is sum modified Laplacian. So this thing we'll use in our lab assignment. So sum modified Laplacian is the formula is like this. So here fxx is dou square by dou x square and its modulus. Then here it is dou square by dou y square and its modulus. Okay, so in discrete form we have to find out the values, no? So so fxx can be approximated as f of, in discrete form we are having discrete images, no? So so fxx can be approximated as fx plus 1 y minus 2 into fxy plus fx minus 1 y. Then similarly fyy also can be written like this. Then this kernel, the kernel corresponding to the first expression can be written like this. Then kernel corresponding to the second expression can be written like this, 1 minus 2 1. Okay, but we have to add these two quantities, no, for Laplacian. So for Laplacian we have to add these two quantities. Then the kernel becomes what? 0 1 0 0 0 1 minus 4 1 0 1 0. Okay, but in the case of sum modified Laplacian we have to use this kernel. We have to use this kernel for fxx of z and this kernel for fyy of z, and for each of the cases you find the modulus, then find the sum to get the SML, and you have to sum it all over a particular neighborhood also. So that also we have to do. So So this is some modified Laplacian. So the first step is you have the image with you. Okay, this is your image. First thing you have to find out fxx of z using kernel 0 0 0 1 minus 2 1 0 0 0. Then you find fyy using the kernel 0 1 0 0 minus 2 0 0 1 0. Okay. Then you find the modulus here. Then you find the modulus of fyy also and just add those values fxx plus fyy. Then you will get some value, no? Then that is to be averaged over a particular neighborhood. That also you have to do. So this is modified Laplacian. So normal Laplacian is fxx plus fyy. So modified Laplacian is mod fxx plus mod fyy, and you have to find out the sum also, and you have to average it over a small neighborhood like I equal to x minus n to x plus n, then j equal to x minus n to x minus n, then this modified Laplacian itself. So you are taking the contribution of the neighboring pixels also. So instead of using only a single pixel, you are taking the information from the neighboring pixels also. So that will help to improve this depth maps. So that is the use of this SML, some modified Laplacian, that you will go through that assignment, then you will get a good idea. Okay. So after getting this focus measure, what will you do? For a particular pixel, say it is pixel 1, you will find the focus measure at every image in the image tag 0, 1, 2, 3, etc. Then you have this focus measure also, and you will plot the focus measure value like this, no? So either you can take this value as the highest value, so you can say that the second at the second image plane it has a maximum focus measure. So we can say that the depth of that image is at the distance of that second image. So distance of the second image means 2 into delta d. Delta d is the distance that we are changing at every step. Okay. So at the so either you can take this 2 delta d as the focus measure, no, not focus measure, as the depth, or we can see here that this amplitude is little higher than this amplitude, no? So two neighboring amplitudes are not equal. So if they are equal, we can say that this is a symmetric Gaussian distribution, and we can say that we can take the center one as the maximum value. But if they are not equal, if the neighboring pixels are not, neighboring focus measures are not equal, then the shape will not be symmetric, no, it will be like this. So we have to fit a Gaussian distribution to get the maximum. So it means that the maximum is not at this discrete position. So we have to find out the exact maximum point. For that only we are using this Gaussian interpolation. Okay. So if this is like this, if the two neighboring focus measures are like this, we can say that the actual maximum value comes here. Is it correct? No. We can say that the actual focus measure value comes here. Then only we can draw a symmetric Gaussian curve. No. So this position only we have to find out. So for that only we are using this Gaussian interpolation, and in the lectures, this d bar was derived using fm plus minus 1, dm plus 1, dm, fm plus 1, dm minus 1, dm. So what is dm? Dm is the original maximum distance that we are getting. Okay, so that value is dm, this value is dm minus 1, this value is dm plus 1, and the focus measures are fm minus 1, fm and fm plus 1. Using these 6 values we can find out this d bar. Okay, along with we have to use delta d also. Delta d also is known to us. So we can find d bar, so that d bar can be associated to that particular pixel. So for every pixel we have to do this procedure to find out d bar. So this is a video shown in the lectures. Here you can see it is a single image only. Here it is a single frame from the video. Here you can see that some of the portions are blurred, but some of them are sharp. Okay, so actual shape of the object is like this. So it is a 3D reconstructed version, and we can find the focused image. If we are capturing the image at any position from the microscope, we won't get a fully sharp image, no, because there is depth difference for this object. So if we are using a simple microscope, we won't get a sharp image. At every image there will be some blurred portions. So if we have to find out the focused image, then we have to find the depth. We have to find out the depth from depth of every point from this image tag. So that depth we will have to find out. Then we know at what frame a particular pixel has maximum focus measure. Then that pixel value we have to copy to the final focused image. So I will explain this. So here we have stack of images 1, 2, etc. 100. Then we are so for the first pixel we are getting that at image 2 it has higher focus measure. So at the reconstructed image, so we will first take a reconstructed image like this, and at the first pixel position we will copy which image patch? Second image patch. So the image patch from the second image we will copy here, and for the next pixel we will search for the maximum focus measure and we will find that it is in the third image, and then we will copy that third image pixel value here, etc. and we will get the reconstructed image. Like that we can reconstruct the whole image. So the question 1 is, for the experiment of shape from focus, an optimum choice of platform step size delta d is. So I have explained this question last week also. So the optimum value of the platform step size is depth of field, because we have to get different focus measure as we when we move delta d apart. No, so in order to get a different focus measure while moving, we have to move more than depth of field. No, so if we are moving very little inside this depth of field itself, it won't give a change in focus measure, because in depth of field everything will be looking like focus. So we have to exceed that movement, we have to exceed that depth of field. So our movement should be greater than that depth of field. Okay, so the answer will be depth of field. Then for the second question, if the focus measure value of a particular pixel is as shown in the figure with delta d is equal to 10 units, what might be the value of d bar? D bar is the distance of that d bar is the depth of the particular pixel. So this image shows a particular pixel's focus measure value. Here in the x-axis it is given that delta d 2 delta d, sorry, it is like 2 delta d, 4 delta d, like that. So first one is delta d, second one is 2 delta d, third one is 3 delta d, fourth one is 4 delta d. Okay. Okay. The question is, what might be the value of d bar? So the focus measures are also given and its value is not given. We have to find out d bar. So we have to use the Gaussian interpolation concept here. Here we can find the maximum focus measure, where the maximum focus measure occurs at 3 delta d, right? So 3 delta d means 3 into delta d. Delta d is 10. So 30. So it will be near to 30 or 30. If these three values are symmetric, then we can say that its depth is 30 itself. But they are not symmetric, no. So here it is a higher value, here it is a lower value. Then something should be between these three lines so that they become symmetric. So the curve becomes symmetric. So that portion will come here only. Then we can draw a symmetric line here like this, and this value is 30 only and this value is 20. So in between the value will be 28. So only value between 20 and 30 is 28. So the answer will be 28 units. So it is not from a calculation, it is by an observation only. Okay. And the next topic covered in the lectures is depth from defocus. So in the previous case we used the focus measure for finding the depth, but here we are using depth. Here we are finding depth using defocus measure. So so for this setup we have to get two images of different focus measure. Okay. So for the same image, for the same object, we are capturing images with two different lens setups. So we are using different lens settings. Okay. So and we are observing image 1 and image 2, and we are taking the patch inside this image 1 and image 2. They are G1 and G2. Here it is by using DFT we can find the Fourier transform G1 G2 is equal to H1 into F and H2 into F, where F is the original, what might be the clean image there, sharp image there, and H1 will be the space invariant blur kernel that causes the blur inside that patch. Okay. So if you are taking a smaller patch, we can assume that it is a space invariant blur. So from this equation G1 and G2, we can find a relation between sigma 1 and sigma 2. Sigma 1 and sigma 2 are standard deviation of the blur inside G1 and standard deviation of blur inside G2. So we can get a relation between sigma 1 and sigma 2 like this. Then we can use the lens parameters like this U1, U2 and WD is a working distance, and this thing we can take it as a blur radius. Okay, sigma 1 and sigma 2. So by solving these two equations we can get a relation between sigma 2 and sigma 1, like sigma 2 is equal to alpha sigma 1 plus beta. So this is equation 2. So from using equation 1 and 2 we have two unknowns and two equations, then we will get any one sigma 1 or sigma 2. If you are getting sigma 1, then substitute that sigma 1 here to get the depth d. So that is this case. Okay, so it is very simple. Take two images from two lens settings. So we know the lens settings and all, and by using equation 1 we will get sigma 1 and sigma 2 relation, and using equation 2 also we will get sigma 1 and sigma 2 relation. By solving 1 and 2 we will get either sigma 1 or sigma 2, and by using sigma 1 we will find the depth d. That's all. So this is depth from D focus. Then the next topic covered was motion blur. So about motion blur, it is already explained from the first lectures also. So which of the following statements are true? Motion blur won't be occurred when the camera is stationary. When both the camera and object are moving at the same velocity, no motion blur will be happen. Motion blur is there in the pinhole camera. So which of the following statements are true? So we can take the first one. Motion blur won't be occurred when the camera is stationary. Whether is it true? When the camera is stationary, motion blur won't be occurred. So this statement may not be true, because when the object is moving, there can be motion blur. So this statement is not 100% true. Okay, provided that there is no object motion, that we have to say. And the next one, when both the camera and the object are moving at the same velocity, no motion blur will be happening. Here, whether the statement is correct? Yes, the statement is correct, because if the object and camera are moving at the same velocity, at the same direction, there will not be any motion blur, because from a particular point of the world, one ray will be hit on the image plane. So there will not be any motion blur. Okay. Then the next one is motion blur is there in the pinhole camera. So we know that in pinhole camera there is no defocus blur. So at different depths, if there are different depths itself, there won't be any blur in the case of pinhole camera, but motion blur can be there in pinhole camera. So the option C is also true. Next question on motion blur. Which of the following are the motion blur kernel PSF? So blur kernel PSF is what? It's like it is a PSF, point spread function, that can be controlled with the input image to get the blurred image. Okay. So what are the conditions of blur kernels? First condition is its value should be greater than or equal to 0. The next condition is summation of the values will be equal to 1. Otherwise, if you are convolving that kernel with the input image, brightness will be changed. No. So its magnitude, its sum which should be equal to 1. So the first case, just check whether all the values are positive. Yes, first condition is obeyed. Second condition is sum of the values in h of n. So 0.2 plus 0.4, 0.6, 1.1. So second condition is false. For the second one, 0.4, 0.4. Okay, so for the second one, all are positive and the sum is also 1. Third one, all are positive and the sum is also 1. Fourth one, all are not positive, sum is actually 1, but all are not positive. So B and C are the correct kernels. So these are all about the topics covered, and this assignment is lab assignment 5. It is also a simple assignment, but in the previous assignment what you have to do is that you have an image, that mandrel image, and you have to use sigma values. You will be given sigma values. So by using that sigma values, you have to find out the size of the blur kernel. and using that size and sigma value you have to find out the blur kernel values, and you have to convolve that using convolve the images using that blur kernel. So here you have to use space variant blur kernel. So here you can say that the sigma values are not constant all over the image. So here you are given two images, globe image and nautilus image. So and at every position sigma will be vary. So you will be given a sigma like this. So in this position sigma is very high. It is given that in this position sigma is very low. Okay. So this type of relation is given in the question itself like this. So sigma depends on the position. Okay. In the previous assignment sigma was a constant. Sigma is already given to you. Okay. So you have two functions in the code, Gaussian kernel and space variant blur. So Gaussian kernel will return a kernel with a particular size. So here it is 3 by 3 no, and the particular sigma. So if you are giving a sigma like 1.6, it will return a size, it should return a size of sigma 6 sigma plus 1. Okay. So it is 1.6, you will get some value of that size no. Then that size and sigma you have to give to Gaussian kernel. It should return a kernel like this. So if the size is 3 by 3, you have to get a 3 by 3 size kernel. Okay, and using that kernel you have to blur the image using SV blur function. So the first step is read the images globe and nautilus, find sigma matrix using the equation. Which equation? Equation is given in the question. Okay, so this equation is given in the question. So for every pixel, so give m equal to 0 and n equal to 0, then you will find the sigma at the first position. Then change that m equal to 0, n equal to 1, second position. So at every position you find sigma. Okay, then you have sigma for every pixel. Then using that sigma find the kernel size and find the corresponding size of the then pass the kernel size and image and sigma to SV blur function. In the SV blur function calls Gaussian kernel to get the kernel for blurring. So that Gaussian kernel will return the Gaussian kernel for blurring, and that kernel should be used for convolution to get the blurred pixel at the particular location. So if you have an image like this, the bigger image like this, and if you have a sigma here, this position, then you will find the kernel like this according to that sigma. Then you will convolve that kernel. It is not a convolution, it is a multiplication and summation only. 1 multiplication and no, 9 multiplication and 1 summation only no. And that answer you have to give to the center pixel. That's all you have to do. So no need to use that convolve 2D function. Okay. Okay, then take the next pixel like this. Take the sigma value there, find the kernel there, find the Gaussian kernel there, and find the product and sum. Then save that to the center pixel. Then take the next pixel like that you have to do. Then you will get a space variant blurred version of this globe. Okay. Then for the second question, you have to verify that if you are giving sigma same for all the pixel, then it is similar to space variant blur. So this is the verification of your code. That's all. Okay, so that's all about this week 5. So do you have any questions? Okay, then we can wind up this session. Okay, thank you.